Scientific notation of numbers. We're going to learn what they are, why they're useful, and how do we convert from a normal number to scientific notation, presentation of a number. So first of all, why they're useful, why we should learn these. Sometimes very, very large numbers and very, very small numbers can be hard to read and understand, and they take a lot of space to write them. Look at this one, for example, 0.000000203. Look at this number. It's rather hard to read it, to understand it. It takes a lot of space to write it, all this space to write this one. And if you have several ones, and then it gets hard to compare them, like you have to count the zeros to imagine you have columns and columns of numbers, and it gets difficult to compare them. So that's why people use scientific notations. Scientists mostly use scientific notation when they're dealing with very large or very, very small numbers, like these ones. Now let's learn how do we convert a number from a normal representation, like these, to scientific notation. Okay, there is a fixed format. Scientific notation has a fixed format, and we're going to learn the algorithm by which we can convert them. Okay, this number can be represented like this. Step 1, scan the number from left to right. Scan the number. When you encounter the first non-zero digit, that will be 2 in this case. So you write down 2, then decimal point, 2 point, and then put down the remaining digits after 2, anything you have. So we have 0 and 3. So I wrote them down, 0, 3. And then multiplied by 10 to the power of, now we have to figure out the power of 10. So scientific notation has a fixed format, one digit to the left of the decimal point, and then whatever digits that they exist to the right side of the decimal point, and then multiplied by 10 to the power of something. So we have to choose the power of 10 in a way the left hand side and the right hand side will be equal. How do we figure out the power of 10? Okay, so for that we need to understand how many digits we moved how many positions we moved the decimal point. We know the original number, the decimal point was here. So we moved it all the way to here between 2 and 0, right? In this new format, the decimal point is moved from here to between 2 and 0. So let's count and understand how many positions the decimal point has moved. So from here to here, that's 1, 2, 3, 4. That's 4, 5, and 6. 6 position. It has moved to the right. The decimal point has been moved to the right side for 6 positions. So our number now is larger, right? 2.03 is larger than this original representation of the number. So now we make it up in the power of the 10. So the power of the 10 has to do something to make this 2.03 smaller. So the exponent of the 10 should be negative 6. 6 for the 6 positions that the decimal point has been moved, and negative because it has moved to the right side. The decimal point has moved to the right side. It has created a larger number, 2.03 versus 0.000, and who knows how many zeros. So that's why we put a negative 6 as the power of 10. Okay, that's how it works. Always one digit to the left of the decimal. Let's practice one more, this one below. Again, we scan the number from left to right. Let's scan. The first non-zero digit is 4. Let's put it down. 4 point, decimal point. The remaining digits copy them. So we have 2, 0, 1. Very well. Multiplied by 10 to the power of something. Now let's figure out that something. Again, we analyze where we have moved the decimal point from here to here between 4 and 2, right? In the new representation of the number 4.201, the decimal point has moved from here to between 4 and 2. Let's count how many positions. It's 1, 2, 3, 4, and 5. 5 positions. So the power of 10 is 5, but is it negative or positive? The decimal point has moved to the right. It has made the number larger, so now we have to make it up in the power of 10 so that the left hand side and the right hand side are equal. So it has to be negative 5. Okay, let's see another example. What if we're dealing with a very, very large number? Look at this one. 313000000. Let's convert it to scientific notation. Exact same process. Scan the number from left to right. Obviously, the first non-zero digit is the first one, so 3. I put down 3. Decimal point. Now, whatever the remaining numbers, there's 1, there's 3. There are a bunch of zeros. Do I need to put the zeros too? No, because zeros after the last non-zero digit after to the right side of the decimal point, doesn't matter if I write them or not, still I have the same number. Okay, so 3.13 and multiplied by 10 to the power of something. Now let's figure out what that something should be. Again, we count where did we move the decimal point. You may say there's no decimal point here, but always there is. So when there's no decimal point, it means it's at the end of it, right? So it's at the end of it. We move this decimal point to here between 3 and 1. Let's count how many positions we moved it. So from here to here, 1, 2, 3, 4, 5, 6, 7, 8. 8 position, we moved it to the left. So the power of 10 is 8. Is it positive or negative? Let's see. We moved the decimal point to the left. We made the number from, who knows, this like 3 million, or I don't know what is this large number. We made it smaller, 3.13. So the number is made smaller. So we have to make it up in the power of the 10. So it has to be positive 8. Okay. Let's see another example. 609020000. Again, a large number. So same process. Scan the number from left to right. The first non-zero digit is 6. Put the decimal point. Copy exactly the same, the remaining digits. So there is 0902. 0902. Do I need to put the 0 digits after the last non-zero digit? Do I need to put these? No, because they don't make any difference. If I put them or not, the numbers is the same. All right, multiplied by 10 to the power of. Now we have to figure out the power of 10. Again, we don't see any decimal point in the number. It's a large number. So the decimal point is at the very end. So we move it from here to between 6 and 0. Let's count how many positions. 1, 2, 3, 4, 5, 6, 7, 8. 8 position again. So 10 to the power of 8. Now you see, if you were to compare the numbers, these two numbers, when they were presented in the normal presentation, it would be hard to tell which one has more zeros, which one is larger. But now we know both of them are from the order of 8, right? This tells us they both from the order, their order of magnitude is 8. Now we know this lower, the number in the below is larger because it's 6 point something. The one in the above is 3 point something. So it also makes it easier for multiplying and dividing these numbers by each other, large numbers by each other. And that is something we'll see in the future episodes. Thanks for watching. Let me know if you have any questions or suggestions in the comments.